Alright, so today we're going to take a look at gravitational forces, specifically looking at solar systems and things like that. So just some reminders, a force, remember, is a push or a pull on an object. Force vectors are talking about those arrows that we see, so a synonym for a vector would be an arrow. And remember, longer arrows equal a greater force, and they point in the direction that the force is either pushing or pulling. And then finally, remember that forces can act at a distance, meaning they're not touching each other, or they can be from two objects in direct contact. Alright, so gravitational forces then are always going to be attractive. So as our moon moves around the sun, we can see these gravitational forces on the right-hand side over here in blue. Okay, and they are attractive. That's what keeps the moon going around the Earth, of course. Well, the same thing is happening over here on the left. As the satellite moves around the Earth, it is also being attracted to the Earth, and we have these gravitational forces between those two objects. So they're attractive forces. Alright, so gravitational forces push down on all objects, and so this is the video on the left that we saw. So the video on the top left, we of course have air. Okay, so there's air in the room here. And so gravity still pushes down on both objects with the same amount of force. However, the air catches the feather, slowing it down. Whereas on the bottom one, that's a vacuum. So they've sucked all of the air out of the room, and when they've done that then, well, that causes then there to be no air resistance. So gravity pushes down on both objects, the feather as well as the bowling ball, in both pictures with 9.8 newtons of force. Okay, that's really what gravity is. So if there's no air to slow it down, they're going to hit the ground at the same time. Okay? So gravitational forces are going to keep objects in orbit. So as you can see here, we have it paused right now, but these gravitational forces are attractive between our satellite and Earth. So this is just going to go round and round in a circle as it's orbiting Earth. Okay? Now this velocity vector is, if we didn't have gravity and we let go of it right there at that instant, that's the direction it would be going. So it's kind of like having a rope between yourself and a rock, and you're spinning it around in a circle. Okay? The reason why it continues to spin around you is, of course, you're hanging onto that rope. Okay? As soon as you let go of the rope, it's going to take off. Well, the same thing is going to happen here if we could somehow turn off gravity. Then it's going to follow this line wherever it happens to be as it's spinning around. Okay, so we're going to unpause it and watch what happens. Okay, so there it goes. Our satellite's in orbit around. Gravitational forces are attractive, so it keeps it there. And then somehow gravity gets turned off, and it's going to continue on in that velocity, that direction, forever. Alright, so what happens if gravity were to completely disappear in our Earth, Moon, Sun situation here? Okay, so around here we are gonna, when I turn it on here, we have the Earth and the Moon. Okay, and so of course the Moon goes around the Earth, and the Earth is gonna rotate around the Sun. Okay, and so what happens is, this is the reason why we have large-scale systems like solar systems and galaxies, is because of gravitational forces. Okay, so they determine the motion of those particular structures. Okay, so without gravity, the Moon doesn't go around the Earth. Okay, and without gravity, the Earth and the other planets don't go around the Sun. So again, if we could somehow turn off gravity, which is what's going to happen here momentarily, then it's going to follow those force vector, or the velocity vector directions, as soon as it was let go. Again, kind of like swinging it around with a rope is really what kind of gravity does. It keeps them together so that they're rotating around and around in a circle. Alright, so this time we're going to look at gravitational forces and how we can change those forces. And one of the ways that we can change that is by changing the mass of that particular planet, okay, or one of the objects that are rotating around. Okay, and so here we have the Earth, and what we're going to do first is we're going to increase the mass. Well, as we increase the mass, just watch these blue force vectors over here on the right-hand side. Okay, so here we go. So we're increasing the mass, and we can see our force vectors increasing. Okay, so greater massed planets are going to have a greater gravitational pull, or greater gravitational vectors. Okay, well, the opposite then is also true. So momentarily I'm going to decrease the mass of the planet if we could somehow do that, and then you should see these force vectors decreasing in size between the two. So smaller massed things like the moon are going to have less gravitational force on them, and so we see our arrows decreasing. Now, why increasing that mass is so important is that's going to directly affect our orbit. So obviously gravitational forces are attractive now. We should be able to understand that. So it's going to hold these things together. Well, if we could somehow increase the mass of Earth here, then that gravitational force is going to increase, and it's going to want to try to pull it in tighter. So you get an orbit that's going to be, of course, closer. And so here comes the moon as it gets closer and closer to Earth there. Okay, and so decreasing that gravitational force causes Earth, in this case, to not hang on to the moon as tightly. So the moon's orbit would be farther away. So gravitational forces directly affect the orbit. And if you can increase or decrease that gravitational force, then of course our orbit's going to go farther or closer, depending on which one it is. Now, other things can also affect that gravitational force. Okay, so you could also then do something a little bit different. So what would be happening if we were to change the mass of the moon instead of the mass of Earth? Well, that would affect your gravitational forces as well. All right, so this time we're going to change the distance between the moon and the Earth. And as we decrease that distance here, watch the force arrows. Okay, so our gravitational forces are going to be affected by that. So here we go, we move the moon closer, and we can see, of course, the gravitational forces between the Earth and the moon is going to increase. Well, the opposite of that is also true. So if I move the moon farther away, then those gravitational forces are going to decrease between the two. So here we go. We can see those force arrows getting less. Okay, so there's less attraction between those two objects. All right, so not only do large objects like planets have gravitational forces between them, like the sun and the earth, or the earth and the moon, or the earth and satellites, but also small objects, so small that they would be kind of like this blue massed object and the red one, which is really only human size. So that every single object, no matter how small, actually does have gravitational forces. Okay, so the only thing is they're so small that they're considered negligible. So if you look at the blue mass right here, well, it has a gravitational force, and so here's its force vector. That's tiny. So look how small that number is. Okay. Well, same with the red one. Okay, so this is the gravitational force between these two objects due to its mass and due to its distance. Okay, but it's so small that it's considered negligible. The same rules, though, still apply for these things. Okay, so as we move these two masses closer together, our gravitational forces here are increasing, and we can see that with these arrows. Okay, so that's what's going on. The same type of information. So most people don't consider gravitational forces to act between small objects, and that's because they're so small that we don't feel them. They don't really have an effect. However, they're still there. Okay, and it still follows those same rules. So we can also change the mass of the object. So as you can see, we're changing the mass of the red object here, and that's causing our gravitational forces to increase, just like what we did with the planets. Again, it's just so small that it is considered to be negligible. Okay, we don't feel them, but they are still present. Alright, so to summarize, gravity does act then between all objects, not just planets, sun, the solar system, but even really, really small objects like a chair, you or me. Okay? And so they all follow the same rule. If mass increases, the force of gravity increases. If the distance increases between those objects, the force of gravity is going to decrease. Now, unless they're really, really big objects like a moon or an Earth or something like that, remember that they're going to be so small, those forces, gravitational forces, that they're considered negligible. They don't have an effect. But we can still measure them. They just don't really do anything. You're not going to feel them.